So welcome, everyone. This morning, I have the absolute pleasure of introducing Dr. John Volkins as the first plenary speaker of this year's AAAR conference. John is a professor of mechanical engineering at Colorado State University and the director of the Center for Energy Development and Health. He holds multiple appointments across the university, from environmental health, biomedical engineering, and the Colorado School of Public Health and the CSU Energy Institute. He's also the co-founder of Access Sensor Technology. So John is a public health engineer, creating innovative solutions to solve public health and environmental health problems. John's research aims to better understand our exposure to air pollution and the adverse impacts on health. To address this challenge, he's pioneered several novel aerosol measurement technologies. These tools have enhanced public health research and practice, from enabling improved exposure assessment and epidemiological studies to also facilitating air quality monitoring in environmental justice communities, as well as for citizen science. John's low-cost yet elegant designs have enabled aerosol assessment even in resource-limited settings. His aerosol measurement technologies have been deployed for public health research in over 40 different countries and as far away as the International Space Center. So please join me in welcoming John.
Thank you, Crystal, and thank you, Amy, for putting together a wonderful program today and inviting me. It's so great to be here. Good morning, everyone. I'm John Volkins from Colorado State University. Let's see here. As Crystal mentioned, I am a founder and equity holder in Access Sensor Technologies. No financial or material support was provided by that entity for this presentation. I do also want to acknowledge the agencies that have funded our research over the last few years, CDC, NASA, EPA, NIH, and NOAA. So thank you. I want to begin with a public service announcement. As Crystal mentioned, I am a public health engineer. That's what I call myself. And the world needs more of us by a large, large margin. If you look at these innovations at the top of the screen, these are STEM discoveries, engineering discoveries, that have had a profound impact on public health over the last century. I would argue millions of lives saved by these technologies, right? And they were invented by people like us. And so as engineers and scientists, we have a huge ability to make a profound impact on public health. It's an incredibly rewarding career. Of course, if you dipped into this at all in the last few years, it's been pretty stressful. We were called upon to serve in many ways, but it's a privilege to be called upon to serve, and we make decisions and do things that help other people live healthy, more prosperous lives. It's really a wonderful outcome. In our field, of course, there are innovations to be made every day, and these are a few of them. If you're not familiar with the technology at the bottom left, that's the Corsi-Rosenthal box, Rich Corsi, formerly of the University of Texas, formerly of Portland State, maybe now UC Davis, I think. The guy's amazing. He moves around a lot. And you can see some other technologies too, like low-cost combustion for use in the developing world, of course, the catalytic converter, and the mask that many of us are wearing today. If you're not familiar with this one here, that's the Chicago River. And it turns out that around the turn of the last century, engineers figured out that they could reverse the flow of the Chicago River if they just poured enough dirt in the right places. This was a profound engineering marvel. As a lifelong Chicago Cubs fan, this means now that wastewater from the city of Chicago no longer flows into Lake Michigan, where the drinking water intakes are. It flows towards St. Louis, which is wonderful. I want to talk a little bit about motivation for my research, and many of you probably know these facts that I'm going to go through, but I'll go through them nonetheless. Exposure to particulate matter air pollution is now the second leading risk factor for premature disease and death on the planet. I call this my grant funding slide. And I apologize that the text is a little bit small, but that's because there are a lot of risk factors for premature disease and death. What you're looking at on this plot On the x-axis is DALYs. That's a fancy word, disability adjusted life years lost. And so what it means is, did you die prematurely from a disease, or did you live a life that was affected by disease? As someone who grew up with asthma, I lived my life affected by a disease, and we can try and count up how bad that is for a person. So scientists and epidemiologists primarily have done this for everything they can think of across the planet. And this is the risk factor for everyone living on planet Earth. And as you can see, I've highlighted, particulate matter is number 2. High blood pressure, number 1. We know that if you go to your doctor and you have high blood pressure, your doctor will intervene that day and try and change your life. But particulate matter is number 2. Smoking's number 3. We don't care about those people. They're stupid. High fasting plasma glucose, right? That's an indicator of diabetes. Most of these things are due to the choices we make. We are not allowed to choose the air we breathe. We have to breathe the air we get. And so when we think about particulate matter air pollution, this is a tremendous amount of disease. It creates more disease and premature death than every other environmental risk factor combined. So what we're doing is important. How bad is it? So this is a slide that I made with the help of Josh Apte and Mike Brower. And what you're looking at here on the y-axis is just a population fraction and then an annual average PM exposure. And then up here we've got some air quality guidelines. And I'm just going to step through some of these countries. India, Bangladesh, Pakistan, China, Nigeria, Indonesia, Europe, United States, Brazil, Russia, Japan, the rest of the world, so we didn't put everyone on here. And then we look at the percent of global population exposed to these levels shown. And what I want you to draw your attention to is that in 2005, we had an air quality guideline of 10 micrograms per cubic meter from the World Health Organization. In this country, it's 12. But just last year, the World Health Organization lowered their guideline to 5 micrograms per cubic meter. And as you can see, only 0.3% of the global population is breathing air at that level. Why did the WHO lower their guideline? It's due primarily to studies like this that just came out this year. This is my colleague Francesca Dominici at Harvard, who has drawn up an exposure response curve for PM 2.5 across the US population. So this is data only on the US. And what you're looking at is the excess risk of mortality, so premature death, as against PM 2.5 levels that we see across the US. This is done as a ratio, so we basically say, all right, the lowest 1% of people in the US are exposed to 2.8 micrograms per cubic meter. I want to know who those people are, because I want to live there. That's amazing. Never seen that concentration, even in Fort Collins. And as we go up, we see increased risk. Now, this might not seem like a lot. 10% increased risk, 1.1. That equates to about 60,000 excess deaths per year in the US. So a massive burden of disease even in this country. And what you can also see is that these confidence intervals about this line don't even cross 1, the reference point, until you're down at about 7.5 micrograms per cubic meter. Well, the World Health Organization is confident that Francesca's data is correct, so they follow the central tendency. And you can see that that doesn't get close to 1 until 5 micrograms per cubic meter. So there's that number. Turns out we still have a long way to go. To manage this air pollution, we have to monitor it. In the US, there is 1 reference grade PM 2.5 monitor for about every 150,000 people. In Raleigh, that number is about 1 for every 500,000 people, because there's only 1 reference grade PM 2.5 monitor that's measuring. I checked the EPA's website before I came here. And of course, it's even worse globally. It's about 1 reference PM 2.5 monitor per million. What do I mean by a reference grade monitor? I mean a PM 2.5 monitor, whether it's filter-based or continuous, that is accurate within about 5%, about 95% of the time. So an incredibly robust, accurate instrument. We're not going to get a lot more PM 2.5 monitors across this country. If you've seen the map, there's a lot, close to 1,000. And so this is the best we're going to do. When you look at a global map, and this is a map made by folks at OpenAQ, a wonderful organization that basically streams all the data they can find on PM 2.5 measurements around the world. They have recently included now low-cost sensor data into their map. And so it's hard to tell the low-cost sensors from the reference monitors. The low-cost sensors are squares, the reference monitors are circles. The point I want to make is twofold. One, most of the monitors are in the US and Europe. And if you look in places where we really need it, like Africa, these are almost all low-cost sensors. So they're providing useful data, but they're not reference monitors. So let's talk about low-cost sensors. They began to show up over 10 years ago, and even longer. I mean, if you call a smoke detector a low-cost sensor, they've been around for decades. But they've really only, in the last 10 or 15 years, started to have sensitivity low enough that we could measure ambient PM concentrations. And so I'm showing a few sensors here. It's not an exhaustive list. But these are some of my favorite ones, mostly because of all the hair that they've caused to fall out of my head in using them. They all work the same way, and they cost between $10 and $50 when you buy them as just the sensor itself. I'm focusing on these sensors because this is what it costs to buy the sensor retail. If you buy a package around that sensor, a weatherproof housing, say a Wi-Fi chip, maybe it's got a battery or an SD card, you're going to put another zero on this cost, and so $100 to $500. That's what I would consider low cost. They all work the same way. They typically have a laser diode to make light, and they have a photodiode to capture light that aerosols scatter onto them. And this is the mechanism by which these instruments count and attempt to size particles. Since these sensors showed up on the market, there have been dozens of products that have followed. This is also not an exhaustive list, but I ran out of room on my collage, so I'm going to stop there. You probably recognize some products here, one being the PurpleAir up here. This operates with the Plantower PMS 5003, actually two of them, which was a smart idea because when the sensors don't agree, you know one of them's broken. And PurpleAir has done a nice job starting to reach coverage of a large area. I pulled this figure off the PurpleAir website just 2 weeks ago, and as you can see, the coverage in the US where it's sold is large, and we can see it's capturing wildfire events in the Pacific Northwest, as we typically see this time of year. We can also see that most of the data coming out of Africa is actually from this network, and there's quite a few in Europe as well and other parts of the country. I suspect there are PurpleAirs in China. They're just behind a firewall and we can't see them. So there's a lot of these monitors out there providing a lot of data. So let's talk a little bit about how these sensors work. If you've worked with low-cost sensors, like me, you've probably gone through a range of emotions and thoughts about how well you think they work. You may have started as a sensor skeptic, like the guy on the left, and maybe at some point you become a sensor enthusiast because you think, well, there's potential to use these devices for certain things. I myself have definitely sat between both sides of the fence, and I'm probably somewhere in the middle now today. I want to talk about really their strengths and weaknesses. To do so, let's talk about optical particle counting, a basic optical particle counter to begin. All you really need to do this, as I showed you in the image before, is a light source and a light detector. We usually put some optics around that light source to shape it and focus it, as you see here. And we've got a light stop over here to prevent excess light from getting into our detector. We then put together some aerodynamics to bring aerosol into the system so we can measure it. And it's important to measure one particle at a time with this kind of setup, and I'll explain why in a second. So as a particle comes in, it'll pass through this beam of light and scatter some light into a detector. And that light is scattered at an angle, and we typically say the scattering angle that we're measuring at is drawn relative to the propagation of that light. And so as I've drawn it here, let's look at that scattering one more time. It took me about 3 hours to make this slide. I'm very proud of it. And it turns out that these instruments, these optical particle counters, they're reference instruments. They constitute a lot of how we do PM monitoring in this country. They're good for sizing from about 0.1 to 10 microns. At 0.1, we just can't scatter enough light to be detected. And at 10 microns, the particles have too much inertia, and we haven't figured out how to properly transport them into this scattering zone without losing too many of them. So you end up with a signal like this, which is intensity as a function of time, right? And we say that the magnitude of the intensity is proportional to the size of those particles, and I'll talk a little bit more about that in a second. The reason you need to bring one particle in at a time is if two particles traverse the beam together, you get a situation like this, called coincidence error, and you have trouble pulling those signals apart. It also turns out that the math of this system has been worked out for a long while. They're called the Mie equations, or Mie scattering. And it would take 3 weeks for me to go through the derivation. It takes a computer about 3 milliseconds, which is nice. But essentially, it's a square law, and so you've got how much scattered light at some angle is proportional to how much light comes in, so how much light you start with, the wavelength of that light, how far you are away squared, so that's that square law relationship. The real action happens with these Mie intensity parameters, these I1 and I2. And we resolve I1, I2 into whether we're looking at light that is polarized with the plane of propagation or perpendicular to that plane of propagation. The point here is that solving these Mie equations can be done by a computer. It's an analytic solution. They're a strong function of things like particle size and refractive index, which I'll get to in a little bit. And so this is the problem we have, because we have one equation and, well, more than one unknown. Let's talk first, though, about how particles scatter light as a function of the angle coming off it. This turns out to be really interesting. What I've done here is drawn that optical particle counter and thrown a 400 nanometer ammonium sulfate particle into the detection zone. And we're looking at the scattering phase function, so how much light gets scattered off that particle as a function of the angle where you're observing it, so that you can imagine these are little rays of light that are being radiated out by that particle after it received this radiant energy. And what you can see is a pretty pattern. This is a log scale I've drawn here. That's really important to recognize. So the particle does scatter some light backwards. I've just drawn relative units here. You don't need to worry about the units here. It's just relative intensity. You can see you've got maybe 10, 12 units being scattered back, but you've almost got 900 units of light being scattered forward. That's an important thing to remember. And as you can see, as you move around to different sides of the particle, you might get different amounts of light. If we change that particle size to 1 micron, we get a neat pattern like this. These leaves or petals in the scattering is due to some resonance that happens as the particle diameter approaches the size of the wavelength of light, and you get interesting harmonics happening. Physics is really a beautiful thing. What I want you to notice, though, is how much forward light this 1 micron particle scatters. Most of the light that it receives, it scatters in the forward direction. Again, log normal scale. We're up in the thousands of units here, and we're still in the tens to hundreds of units at the side. You know this phenomenon in your own life experience. Because if you ever are near a rising or setting sun, it will illuminate the aerosol in the atmosphere around you. As you can see here with a father and what I presume is a son walking on this dusty street, and all of that coarse aerosol is being illuminated because it scatters light in the forward direction effectively. So whenever you have the sun pointing just off your eyes, you will be able to see particles in the atmosphere. And so in the morning light or at sunset is a great time to visualize aerosols. So forward scattering is important because these particles love to scatter in the forward direction. The theme for my talk this morning is going to be me complaining about the fact that we've known this forever. This is an elegant design of a forward scattering detector published by Sinclair over 50 years ago. So we have known how to do this for a long time. This design, you can see we're just taking light. We're actually removing light at the center line, so we only have this light on the outside, so we expand it through a series of lenses. It then gets focused onto a particle, and then it expands again. What's nice about this pattern is that only light that is scattered in the forward direction is measured by the detector. None of that incident light is measured. What an elegant design. We've known how to do this for 50 years. So the amount of light that aerosols scatter depend on the size, their shape, the refractive index of the particle, the wavelength of light, and the scattering angle. There is a lot going on here. But it turns out that when we make these systems, we can typically set a lot of that stuff constant, and we're typically then left with dealing with the size of the particle and its refractive index. We want to get particle size. That's important to us. We're aerosol scientists. This is some nice work done by David Hagen and Jesse Kroll, published last year, that essentially looks at the scattering intensity, so how much light is scattered on the y-axis. And if you're not familiar with these units of centimeters squared per particle, it seems a little odd. This is a ratio of how much light is incident to the particle per unit area of the particle. So the particle has some cross-sectional area and light's impinging on that area, relative to how much light is scattered away. So that's why it looks almost dimensionless, but it has units of centimeters squared. If that doesn't sit well with you, just think about this as an intensity axis, and notice that it's log scale and varies about 6 orders of magnitude. So it's massive. 6 orders of magnitude of variation across a particle size range from 0.1 to 10 microns. What you also can see here is that when you look at different types of particles, so they've basically colored these lines, these response lines, as a function of whether you're looking at polystyrene latex, ammonium sulfate, SOA, brown carbon, black carbon, you can see different responses. This is the issue. What manufacturers typically do is just throw a line in the middle of those curves and hope for the best. And when you do that, then we're going to try and figure out particle size. So what you would do is the instrument would measure the scattering intensity, and you'd come over here to your calibration line and say, oh, well, that's about a 1 micron particle we've got there. And so that's how you'd figure out the size of your particle using an optical particle counter. Of course, when you look and you allow refractive index to vary, as I've done here, you can see that the uncertainty in that measurement is almost 1 order of magnitude. This could be a 0.5 micron particle, or it could be a 3 micron particle, depending on what it's made of, because of its refractive index. Might I add that we also don't know the density of the particle. This is important because we're almost always interested in the mass of aerosol, because mass is what's regulated by the Environmental Protection Agency. And because epidemiologists have shown that it's PM2.5 mass that seems to be the driver of all these adverse health effects. We can't figure out what else about particles besides their mass in this size range is important for health. At least not enough that we can convince EPA to change their laws. There's another technology I want to talk about before I talk about these low-cost sensors, and that's called an integrating nephelometer. This works similarly but slightly different than that optical particle counter I showed you. For this nephelometer, we actually bring in a lot of aerosol at the time into this measurement cell, this white area I'm showing here. So here are those particles. And then we've got this flash bulb that produces light, so it illuminates most of this measurement cell. Now, to understand how this device works, we only actually need to look at a few cases of where particles sit inside the measurement cell. When you think about particles over here on this side, watch the light they receive. They only receive light in this direction and scatter it, because of the optics here, only in the forward direction. So particles in this part of a nephelometer, we measure their forward scattering light. Of course, particles in the measurement cell over here, we measure their 90-degree or side scattering. And particles on the back end, we measure their back scattering. What that means is that this instrument is capable of measuring scattering over almost 180 degrees. And since the scattering function is typically symmetric across that, we've measured all the light that these particles can scatter with this instrument. Turns out that this is really useful, not only for estimating things like visibility in the atmosphere, but estimating mass concentration. I would hypothesize that aerosol scientists are not leading the development of low-cost PM sensors, because if we were, these sensors would be better. And I'm going to show you what I mean by that. We can develop things like physical optical models of existing low-cost sensor technologies. And when we do that, we find out that these technologies are truncated nephelometers that count individual particles. So they kind of draw from both the optical particle counter and the nephelometer in their measurement principle, but they don't do either well enough to really be satisfactory. And I'll show you what I mean by that. So I'll pick on the SPS 30. It doesn't matter which sensor I show you today, they all kind of operate the same. When you take this device apart, you will see, all right, there's the laser. There's a little fan to draw air. We've got an interesting geometry in here. We can zoom in on the aerosol sensing region. And so you've got a little mirror and a photodiode here. There's that light. We think the light is being focused into some region here. We know that just by looking at the geometry. When we reverse engineer this device, we can figure out what IO is because we can take this laser out and look at it. We can figure out theta because we know what this measurement region is, and then we can basically simulate a particle sitting anywhere in that measurement region. And once we do that, we can figure out then how much light it's scattering. By the way, this is work that was done by my colleague Jim Ouimet, Bill Malm, and Brett Schichtel. And he's also done this for the PurpleAir sensor, or the Plantower PMS 5003. So he's now done this a couple times. The point being is that once we understand this geometry and the power of this laser, we can figure out how much light we expect particles to scatter as they go through the device. How do we know that they're counting? Because we can hijack the circuit board, we can pin into it right behind an op amp and watch on an oscilloscope particles being counted as individual scattering events. So we know that they do these things. So what we find, and I mentioned this before, is that these low-cost aerosol sensors are truncated nephelometers that count individual particles. What do I mean by truncated? If you look over here on this picture, you can see that if this is the measurement region, only a particle at the front end of this measurement region could actually scatter any forward light into a detector, and it's not a high degree of forward scattering. It's about, 30 degrees. It's outside the region where we get that strong forward scattering signal, where all the light really is from larger particles. These instruments are leaving a lot of light on the table. So by truncated, I mean that we don't have 180 degrees to draw light from. We're truncating down in angle, and we only have maybe 30 to maybe 150 degrees. Backscattering doesn't turn out to be as important for these particles, so it's really forward scattering we're trying to capture. These devices don't do that. How do I know that? We can create through our physical optical model a prediction of how much light is left on the table by these devices. So here, I'm showing a scattering ratio on the y-axis. A perfect nephelometer, that device that can do 180 degrees, would be a flat line across the top. It measures all the light that scatters. This Sensirion SPS 30 measures a lot of that light for smaller particles like 0.1, 2, and 3 microns because they tend to scatter light more equally in all directions. But as particle size grows from 0.3 to 1 micron, those instruments leave a lot of light on the table because most of that light is being scattered forward and they don't see that light. We've created a lot of different particles in the lab and counted them with reference instruments. This is that, so when I say truncation error, I'm referring to this lost light. And when we compare these instruments to our reference instruments, we see things like this. So now we're looking at lab data where we've taken ammonium sulfate of different size or NIST PM2.5 of different size, PSL or wood smoke. It doesn't really matter. You can see that as the refractive index and size vary, we capture that loss of counting efficiency very well. It's not perfect because the model's not perfect. The reference instruments aren't perfect. Our size distributions aren't perfectly monodispersed either. But you can see as you go from particle size increasing from about half a micron up to 1, we see this massive loss in signal. And it kind of just starts to bottom out once you get to 2 microns. So lab data agrees well with model predictions. We're not the only folks to show this. This is work done by Kula et al., published in 2020. Laboratory evaluation of particle size selectivity of optical low-cost particulate matter sensors. I want to highlight this paper because I have an academic crush on this work. These guys unlocked the cheat code for the TSI VOAG. If you've ever used a TSI VOAG before in your lifetime, it's the closest you will come to experiencing alchemy in science. It's got all these knobs and buzzes and lights on it, and you turn them and push them, trying to get this little vibrating orifice to spit out monodispersed particles. If you manage to get that to happen, you tell everyone in the lab to leave. You collect data on one particle size, and then you go for beers, and you come back the next day and try it again. I've had the pleasure of working with this instrument. It's now semi-extinct. I think TSI has canned it. But these guys figured out that instead of flowing a constant solution to the instrument, you take 2 syringe pumps and you flow a gradient solution over time. So that when you get it to magically create 1 particle size, Over time then, a particle size distribution of monodisperse aerosol will evolve out of the instrument. So you only have to get it to work once, and then you can do all your measurements in a day. I was flabbergasted when I read this paper. This was me. So what did Kula find? You won't be surprised to see that they found similar results to what I just reported. What we're looking at here on this plot is a normalized detection efficiency on the y-axis as a function of the count median diameter of those particles. They used an APS, so it starts at 0.5 microns. But you can see a similar sharp drop-off in counting efficiency. Now, this plot may confuse you a little bit because it's colored by size ranges that the manufacturer reports the device can measure as far as counting particles. This looks a little confusing. Let me help you out. Let me show you what a reference instrument would look like on this plot. Okay? A reference instrument would have a high counting efficiency in the particle size ranges that the manufacturer claims to achieve. What you see here is something very different and very similar to what I showed you before. What this means is that these low-cost sensors have a fair ability to count 0.3 to 1 micron particles in here, a pretty poor ability to count 1 to 2.5 micron particles, and virtually no ability to count 2.5 to 10 micron particles because of that truncation error that we discovered from the physical optical model we developed. Go outside and take these measurements, you see the same thing. This is work we collected at CSU over the past year or so. And what I'm showing you is now 3 different sensors to prove that they kind of all work the same way. The Piera, the Sensirion, the Plan Tower, this is what's in the PurpleAir. Don't worry so much about looking at the summary statistics. Let your eyeballs do the talking on these plots, okay? When we look at PM1, the sensors actually, they aren't bad, right? You can see pretty good agreement. The color is summer versus winter, and so aerosols change their refractive index, their composition over seasons, and so we see some variation there. When we move to PM 2.5, it starts to get a little shaky. At PM 10, it gets really bad. The only reason there's any agreement here in PM 10 is because PM 10 is constituted by PM 1. How do I know this? Because when we look at PM 1 to 2.5, we see almost no agreement. And when we look at PM 2.5 to 10, we definitely see no agreement. All right. Not great. Well, what can these sensors do well? Well, it turns out that they can estimate mass concentration of accumulation mode aerosol across a really wide dynamic range, like 3 to 3,000 micrograms per cubic meter. Caveat, when they're calibrated to an aerosol of interest and that aerosol remains stable. That's the key word. Stable in refractive index and stable in size distribution. So if that happens, you're golden. What this means is that a lot of people, a lot of you, have spent a lot of hours trying to figure out how to make these instruments better. What you typically do is co-locate your low-cost sensor with a reference instrument for some period of time. These instruments put out a lot of data and it's messy. I can't emphasize how important data science is to this, this pursuit. And so programs like Python, R, or Julia, we use R in my group to manage this data. There's a lot of it that needs to be cleaned up. We do some sort of calibration to figure out why the sensor disagrees with the reference instrument. And if we're doing a good job, we'll deploy those instruments then and we'll validate how well we think our calibration model did. So as I mentioned before, lots of people have done this. There's some great discussions out there on how to do this well. It really comes down to, as Kirsten Kohler's group suggested in AMT this year, you have to calibrate to the conditions you expect to see in the field. And whenever that aerosol size distribution or refractive index changes, you're going to expect error. I'll highlight friends at CMU who have done some great work. They have been collecting data with these PurpleAir sensors for a while, and they have thrown the veritable kitchen sink of calibration methods at that data over time, all with the thought of how low can you go in error. So what you're looking at here is PM 2.5 concentrations reported by a PurpleAir, which is really the Plan Tower PMS 5003, against a reference instrument. And you can see there's quite a bit of error for PM 2.5, not a great R squared. Mean absolute error, MAE is the one I'll focus on. There's lots of ways to categorize the performance of these devices. I like mean absolute error because it's in the units of the data you're collecting. In Pittsburgh at this time, you could expect mean concentrations around 10 micrograms per cubic meter. So this is about 40% error on average in one direction or the other that we're seeing. You will also note that they've colored this data by relative humidity. That makes sense because particles like to take up water, and so they grow, and so they get more error as relative humidity goes up. EPA doesn't care about how much water you inhale. They regulate dry PM 2.5 mass, probably for good reason. Otherwise, people in the South would all be in violation, at least in the summertime. And so what they first did is they said, okay, let's just create a binary multivariate linear regression model. And they looked at tempering varying parameters, things like temperature or relative humidity or dew point. Bivariate because they figured out that the instrument has differential response below 20 micrograms per cubic meter and above 20 micrograms per cubic meter. The lesson here is that manufacturers can do whatever they want inside the device to change its output, and they don't have to tell you about it. We know now that this instrument kind of has a two-pronged calibration for some of its data signal, and that's why they developed this multivariate correction. When they do that, they take the mean absolute error for this instrument down to about 2.5 micrograms per cubic meter. So they've gone, or 3. So they've gone from 40% error to 30% error on average. They can also use spatially varying variables. Things like, is the sensor near a major roadway? Or is it in an industrial park? Or is it in a field? Or is it near a farm? How much traffic flows by the sensor on a given day? That's called a land use regression model. So instead of these temporally varying things, they look at spatially varying things to predict error in the sensor, and they do about the same. If you don't really care about, or you care less about interpretability, you just want to get the right answer, you can throw machine learning at it, and typically that gives you the best result. You can maybe get that error down to about plus or minus 20 or 25%. Not bad. I also want to highlight this work done by Barkjan at the EPA. Most of the calibrations we see are for one city and one season, and that data is probably not generalizable to another city and another season. But Barkjan said, well, look, these PurpleAirs are all over the country. Let's develop a simple correction equation for them so that we have a national correction and help out the PurpleAir company so that people using their data will have more reliable data. This is just a 3-parameter fit, or really a 2-parameter fit if you consider the intercept. It basically says that the PM 2.5 concentration that the sensor measures, that the sensor reports, needs to be multiplied by 1/2 and corrected for relative humidity. So the sensor overestimates PM 2.5 mass by a factor of 2. And whenever relative humidity rises, you need to reduce it because those particles are growing due to water. What's amazing is that when you do this correction, this really simple correction, for people using the PurpleAir network, this correction gets the air quality guideline, so the color, green, yellow, red, it gets it right 90% of the time. This is great because for people in need who want to know what's in the air I'm breathing, is it healthy? The correction is great. Now, maybe not for researchers like us, we want a higher level of accurate precision, but for many people across the country, the sensor can be corrected to provide actionable data. If I have asthma, should I go outside? Our physical optical model can actually show us why these values are what they are. Let me talk about that for a second. We'll start with the relative humidity correction. If you know anything about aerosol hygroscopicity, or how particles grow when relative humidity goes up, you know that it should be nonlinear. It should follow basically a curve like I show here on the right. So now I'm showing the aerosol mass ratio, so how much the wet particle weighs relative to the dry particle. If a particle does take up water, and most particles in the atmosphere will, if you turn the humidity up high enough, they will grow exponentially, which means that their mass will grow exponentially as well. This is, of course, how clouds are made. Clouds have a lot of water in them. So we see a relationship like this, and yet the Barkjan paper said, no, it's just a linear correction. That's all you need. So this made me scratch my head when I saw it. The reason, actually, though, is because of this truncation error. So over here on the left, I'm showing you now the mass scattering efficiency. So it's the light scattered per unit mass of the particles, since that's what we're trying to measure. An ideal nephelometer has something that looks like this when you solve those Mie equations. The PMS 5003 leaves a lot of light on the table. And so as particles are growing in the PMS 5003, they don't scatter as much light. In fact, when we look at this in the lab, how much light they scatter as they grow, we get data like this. Whether you fit this to a linear or a nonlinear term doesn't matter to a statistical model. The error is the same, so you always go with a simpler outcome. This is why a linear correction turns to work out well for these devices, and it goes against what we think for theory. You wouldn't know this until you create the physical optical model, of course. How about this 0.5? This is actually easier to explain. PurpleAirs were calibrated in China, not in the US. When we look at global aerosol size distributions, so I just pulled this paper. This is just a bunch of data from China, and I've drawn an eyeball line through it. I don't think we need to do any better. Here's data in the US. I've drawn an eyeball line through it. We kind of know that mass median diameters, so average mass particle size in the US is about 0.3 to 0.4 microns. That produces a mass scattering efficiency of 2.5 meters squared per gram. In China, mass median diameters are on the order of 0.6 microns. That produces a mass scattering efficiency of 5 meters squared per gram. 5 divided by 2.5 is 2. Right there. We're just measuring a different aerosol than we calibrated on. I can prove that to you because when people look at these plant tower sensors in Beijing, they work great. They don't need to be corrected as far as their slope. They're still noisy, of course, because aerosols in Beijing change just as much as they do in the US, from day to day. But you don't need to do that 0.5 correction over there. All right, so I've been picking on these low-cost sensors, but I will say they can provide actionable data for crowdsourced science, environmental justice, and communities in need. We don't always need to be accurate within 10% of truth to make informed decisions, which means we can use these devices not only to do science, but to help people out. I'll highlight some work done by colleagues at Berkeley. They leverage this PurpleAir network, so this is crowdsourced data. The top plot shows indoor PurpleAir monitors, so people wanting to know how clean the air is inside their homes in the Bay Area. This one shows levels outside. And you can see that essentially what they find with a simple mass balance model is they can figure out the infiltration ratio of outdoor air pollution into homes and buildings across the area. Most epidemiologic models, when we look at the health effects of air pollution, don't take this sort of information into account. So it's really valuable information that we're doing science. This was published in PNAS last year. They also showed that when wildfire smoke enters the Bay Area, people react to it. And they try and seal up their homes or make their homes cleaner. And we can see that very clearly because the infiltration ratio gets lower during wildfire events. Again, this is really cool science that's being done with these low-cost sensors. I will also point out, however, though, that Odell this year pointed out that most of these PurpleAir sensors are sitting in homes of affluent individuals. So there's still a lot of work to do because even at $250 or $400, these sensors are not in the backyards of people who need them most. Something to keep an eye on. Having said that, the research is really expanding in this field. So this is just a Google search result for community-based, low-cost monitoring in PM2.5. That's a lot of words, and still you can see we've got hundreds of papers. I'll now spend the next 10 minutes going through each of these papers individually and telling you about their strengths and weaknesses. No, I can't do that, but I do want to highlight a few and just kind of point out what can be done with these monitors. This is work by D'Souza et al. This is Nairobi. This is a map of Nairobi. What D'Souza et al. Did is they put these instruments on vehicles, drove them around the city of Nairobi repeatedly, and created a map of what they thought PM2.5 levels were during the pandemic. And as you shouldn't be surprised, the affluent neighborhoods, with this box on the left, show a 300% difference in PM2.5 concentrations relative to the poor neighborhoods on the right. This is largely due to how people use energy in their homes. This is solid fuel combustion, so there are campfires is how you have your light and heat. And over here, it's probably electricity or cleaner versions like LPG. You don't need to be worried about 30% error when you're looking at a 300% difference. Environmental justice is a log normal phenomenon. And what I mean by that is we don't look at differences that are plus or minus 10 micrograms per cubic meter. We look at differences that are like 200% oftentimes with environmental justice. These sensors, we can trust them to do that kind of measurement. We're also getting data from these sensors in places where no data came before. Places like Africa and Asia, countries that don't have reference monitors. There are now PurpleAirs being calibrated in those regions, like the Congo, where we see data for the first time ever. That's really valuable. In the Arctic or in rural areas, I mentioned that there's one PM2.5 reference monitor in this country for every 150,000 people. If you live in a rural area, there isn't a PM2.5 monitor within 50 miles of your home. Or for wildland fires. So this is something in the West we deal with now on a more common basis. We don't put PM2.5 monitors out in the wild. And when fires erupt, we don't know what ground level concentrations are. And so we can use these monitors to inform that sort of monitoring as well. Looking forward, what are the prospects and priorities for these technologies? Well, the first thing I'd say is let's build a better one, because we could do a lot better. The next generation of low-cost sensors could be amazing. If you have more than one equation and more than two unknowns, get yourself some more equations. Add more scattering angles. This is really easy. The design exists already to do this. We could do forward scattering in these devices, and we could clean up all that truncation error. We could use two and do multi-wavelength. That's possible as well. And I recognize maybe some of you have thought of this, and you're working on it. Great. Continue. And of course, we need to minimize aspiration and transmission losses if we really do want to do the former two and reach PM2.5. I can tell you that this is not happening yet. Let us help you, manufacturers. This is the real challenge. Why? Well, there are devices, and I'll get to that. There are devices out there like this AlphaSense OPC-N3. It costs $500, which means if you buy it in a package, it'll cost $5,000 or $10,000. So it's not quite there yet. And it doesn't really do any of these things, but it does measure forward scattering light and more effectively. So we're kind of getting there. Will we go farther is my worry. We, as a community, are not the target demographic for the sales of these devices, despite how great we think we are. I've shown here market estimate size for air quality monitoring. It's estimated to be a $4 billion market globally. That's large. But it's 4 times smaller than the HEPA air purifier market, and it's 50 times smaller than the building ventilation market. They are making these devices for these people, not for us. We still have a lot to learn about personal exposure. This is an area where these devices can also be used. We've come a long way. This is an image. This is the oldest personal exposure monitoring with a real-time sensor I can find. It's from 1982. Not only does this poor sod have to work in a beryllium factory, but he has to carry 50 pounds of real-time aerosol instrumentation on his back just to estimate mass concentration. So this was 1982, how we were doing it. By 2010, we'd gotten the backpack smaller. And the instrument had gotten a little smaller as well. So this is kind of a similar kind of truncated nephelometer, like those low-cost sensors. Today, this is research from my group in the center. We are putting these devices in little wearable PM measuring instruments. We like to collect a filter whenever we collect a light scattering signal because we trust mass. It's a challenge to get enough mass on that filter, but we do it with technology like this. And of course, if you don't care about accuracy and precision, you can just have the low-cost sensor itself and buy it. We know that our personal exposure, the PM2.5 that each of you is breathing on a day-to-day basis, varies incredibly. This is a plot showing participants, about 50 people in the city of Fort Collins, and it's showing their average PM2.5 exposure for a day. And it kind of matches up with that curve I showed you before, about 5 to 20 micrograms per cubic meter. So you see a lot of variation. I will point out that these averages are 8 different days across the year. Now, what I also want to show you, though, is just one participant, number 25. Look at and we're looking at we've apportioned this with GPS tracking and some other sensors where they got their exposure, home, work, transit, eating out, or some other location we couldn't figure out. There is massive variability from day to day for one person. we have almost no way to predict PM 2.5 exposure. The best models, machine learning models, they have an R² of around 0.5. So this is where we need more data, and these low-cost sensors can help us get that data. We also need to know what aspects of PM 2.5 matter most for our health. So I showed you this curve before, right? It's the low-dose exposure response for PM 2.5 from Francesca Domenici's group. EPA is going to have to lower the NACs in the coming years because of this plot. This is a big deal. And if they don't lower it themselves, they're going to be sued by folks like the American Lung Association. And the American Lung Association wins most of their lawsuits against the EPA, okay? That's because the Clean Air Act is a really nice piece of legislation, and it's hard to invalidate. So lowering the NACs will be a challenge. Achieving those lowered NACs will be even harder because the costs get exponentially larger as you try and lower below 12, 10, 9, 8, 7, 6 micrograms per cubic meter. So we need to answer the question, what about PM 2.5 is most bad for our health? Now, I've just drawn common components of PM 2.5, at least in ambient air here. I think we'd all agree that we don't want to be sucking diesel soot anytime soon. But there's also things like sea salt, oleic acid, or olive oil from cooking. There's ammonium sulfate, and there's SOA. Which one's the worst? Or maybe they're all equal. I can tell you that we've spent about $1 billion on this question, and we haven't gotten any farther to knocking PM 2.5 mass off the regulatory armrest. I will also note that low-cost sensors can't make any of these distinguished measurements yet. They can't distinguish these sources apart, and they need to be able, if we're going to be understanding why PM 2.5 is bad for our health. This is a huge research area, and I think we have a contribution to make to it as a discipline, because we understand this stuff. A study like the one I showed you before, this is work from Canada. It's a similar study, but now I'm just showing you those exposure response curves by region in Canada. This is from Mike Brower. What you can see is as PM 2.5 increases, your risk goes up, but it changes by region. Now, these studies control for everything like how wealthy you are, what's your education status, the season and weather patterns that exist in that area, whether you live near greenness or not. But they get different exposure response patterns. The one thing they don't control for is the aerosol mix in these regions, and it varies from location to location. Again, I think we have contributions to make to this really important field. And if we get more involved with those epidemiologists, if we cross our disciplinary boundaries, I think we can get there. So that's my closing statement to you. Thank you.
Well, thank you, John, for a fantastic talk. So I encourage you to come up to the microphones if you have any questions.
Okay, let me know when I'm done.
Well, interesting talk. This is Xiaoliang Wang from Desert Research Institute. I want to comment that the underestimation of the low-cost sensor is not because they are truncated nephelometer. As one of your slides show that even for an ideal nephelometer, the mass scattering efficiency drops as the particle size go up. I think the key is that these sensors does not seem to be counting these individual particles. Like the dust track DRX, it actually does count the individual larger particles on top of the nephelometry measurement.
Yeah, I do agree that they don't have efficient counting, but that is usually handled by a factory calibration, so we know that they miss a bunch of particles. And you're also correct that when you go above 1 micron, even for a nephelometer, you get that loss. It's just that mass median diameters rarely get up to 1 micron in ambient air, and so we're still on the truncation side when we go from 0.3 to 0.6. But you're absolutely right that if you went above 1 micron in particle size, then the nephelometer would also start to lose its signal. Sure, over there, and then go.
So when you spoke about the light scattering setup and using it to retrieve the particle size, there are secondary unknowns in refractive index and density of the particle. Now, how practical is it in these sensors to use like 3 light sources which have different wavelengths so that if there is a dependence on lambda to the fourth, a 10% change in wavelength is about 45% change in intensity. Would it allow you to retrieve 3 of the unknowns simultaneously?
You would need multiple angles and multiple wavelengths, I think, to fully constrain the problem effectively. Yeah, I'll leave it at that. I mean, there's lots of ways to skin that cat, and there are instruments that can do that. They're just not low cost yet. Yeah.
Thank you.
Fantastic talk.
Thank you.
I have a shameless plug followed by a speculative question. My name's Sherry Pilkington of IARPA. I'm a program manager, and I am setting up a new program called Picard that is addressing low-cost sensors that can do chemical characterization along with physical size measurements. So I would encourage everybody to look at that and provide feedback so we can do a good job. My speculative question is, do you have any thoughts on developing low-cost sensors that can handle non-spherical particles and how that can be kind of accounted for in these devices?
Yes, that's a really good question. As my colleague Tammy Bond always reminds me, black carbon is not a sphere, and you can't assume that it is when you try and solve the Mie equations. That does contribute to uncertainty in the size measurement. The good news is there are physicists actually working on these problems. And so I mentioned Jim Ouimet and his colleagues. They are now trying to solve the Mie equations not for simple propagated light, but like a Gaussian plume, right? So a focused beam of light, at how it actually looks when it goes through the optical particle sensor. So they are working on these problems. I don't know if they're going to get to the shape effects anytime soon. What I will say is that shape effects don't seem to be as big of a driver as particle size effects and refractive index effects. So it's a secondary or tertiary concern over the long run. Yeah. We'll go here and then in the back.
Thank you for the great talk. So I am Maria King from Texas A&M University, and my question is that do these local sensors collect statistically significant volumes of air for the particle content to be determined?
Yes, they actually, there is a lot of engineering that goes into these devices. And they flux actually a large amount of air through that sensing volume. They typically flow at like 1 to 2 liters per minute. And they have a very small internal volume. And so one thing they do well is the electronics inside the device can count particles really, really quickly, like microsecond quickly. But they still suffer from all those other issues. So I actually don't think that the flow rate through them is the big issue right now. I mean, there isn't a lot of flow control. So if we could get that under control, it'd probably get even better. But they do bring a lot of particles, and so they do a lot of counting. It may become a problem if we get these devices to be good enough to measure things like PM10, because the number concentration, we're ultimately counting particles, is way, way, way lower for those. And so we may need longer integrating times to do larger particle sizes. But you just wait longer, so you don't get data every second, you get it every minute. That's still pretty fast.
Thank you.
Yeah. Hi.
Thank you, John, for the great presentation, and especially bringing back the engineering, the fundamental work. And as a mechanical engineer trained and turned environmental engineer and then going on to 5 years of public health postdocing, it was the same kind of impetus trying to find out that link between air pollution and health in the instrumentations and the work at the fundamental level that can get us to finally get health for some of the most disadvantaged people. Now, we got different directions because, as my career have turned out, it hasn't been that easy to be what you call now the public health engineer. Well, I'm more on the other end where I want to be an engineer fixing the problems of public health, which are not going to be solved with instrumentation per se, but we do need the instruments to be correct. So thank you for the work that you've been doing. I want to talk about the part regarding what we're going to do with this data, or where it can be actually useful and meaningful, and that is addressing the problems of environmental justice or injustice, which is not only in the US, but it's all around the world, as you know. In this very conference during the pandemic, because we're not done with it, We're going to have several events dealing with environmental justice starting today with the book discussion. Tomorrow, a panel where we're going to talk about community engaged research, which is some of the work that people like myself have been doing for decades, literally, and have not been recognized as important. And certainly, it's about time that we give it to time and recognition. So I want to invite everybody to attend these events because behind all of this science that we need to do is human need, and we need to finally get to the point where our science is meaningful and useful. I wanted to make sure that everybody knows Wednesday, tomorrow already, at noon, we're gonna have the panel discussion on how we're gonna create a community-engaged research community. And finally, just wanna say that our audience, we need your contributions, and please support the work that scientists of color do in this community, which is usually not what we get. It is really problematic. So we're hoping that we have some discussions started this year after you have seen the statistics. When pandemics hit, when the fires hit, people who die are the people of color in this country, and having been one, if not one of very few of them in this community, literally for decades, predating some of the people who are presenting today. It is time for change. Please pay attention, especially the young people. We have been doing work in here trying to correct things and do things. So I'm glad when, finally we're paying attention to the accessibility of instrumentation. Thank you again, and I hope to see you guys at these events. We have another event on Thursday. And please feel free to, approach me anywhere. My name is Lupita Montoya, formerly at Stanford, then Harvard, and then Rensselaer, recently University of Colorado, from the state from which I ran for my life, because unlike other people, I was not welcome with my science there. And now I'm presently doing a Fulbright year in Mexico where I can do some science and hopefully not fear for my life for a while. Thank you very much.